Folks, this is it. 10 out of 10, best video ever. No, 10 out of 10, the last video on this topic. Sorry. Hopefully the best video ever. I'm going to do my best. This is about uncountability, about being bigger than the naturals, right? That's what this video is about. So we've already seen in the last video what it means to be countable, right? To be no larger than the naturals. We're going to say a set is uncountable when it's strictly larger than the naturals, when there's more of those elements in your set than there are natural numbers. That's got to be a huge set, right? Because we already saw like some very big sets, some surprising sets are countable. The integers, the rationals. So what's going to be uncountable? In this video, I'm going to show you two sets that are uncountable. One is functions from nat arrow nat, and the other will be the reals just on the interval 0 through 1. The whole reals are much bigger than that. There's a really cool theorem that you can learn in topology that show that the reals are the same size as the reals on 0 to 1, but we're not going to bother with that because, the real numbers, they call, if they were really real, would they have to call them that? It's like calling a dish famous on a restaurant menu. Right? Like, if it were so famous, wouldn't I know about it? Like, why do you need to tell me? So if there's such real numbers, why don't you show me one? Anyway, that's my own personal prejudice. Let's continue. These are the two examples we're going to do. The general idea is we're going to use a proof method called diagonalization. Due to my man, Georg Cantor. It's a super cool proof technique. You'll see it again in 101. That's kind of why we teach it here. But it's just an incredibly powerful technique to have in your toolbox. Okay, so let's start. Let's think about nat arrow nats. Theorem. This function space, the functions from nat arrow nats, is uncountable. Strictly speaking, I would say the set is uncountable, not its cardinality. All right, that set is uncountable. Proof. An arrow n is clearly infinite. For example, here's a function f from nat to nat arrow nat. F of n is just, and I'll use cock notation here, fun, whatever, n, right? For every natural number, there's a constant function. Okay, cool. So we know, it's very clear, like this function is injective. So that means that it's very clear that the cardinality of n is less than or equal to the cardinality of n arrow n. But is it the case that the cardinality of n arrow n is less than or equal to the cardinality of n? So we will show, no. Okay, so to do that, suppose for a contradiction, that there exists a function, call it g, from nat to nat arrow nat, surjective, right? That would suffice to show that the cardinality of nat arrow nat was less than or equal to the cardinality of nat. Okay, what does this g do? So g, if you like, you can kind of think of as a table, and this is where the relations view of functions comes in handy. So g basically says 0 is going to map to some function h0, and 1 is going to map to some function h1, and 2 is going to map to some function h2, and so on, right? And then for it to be surjective, every nat arrow nat function accounted for. Cool? Okay, so I'm going to give you my function. Oh, oops, let me write it in black. So I'm just going to name a function, and the way my proof is going to work is I'm going to say, oh, well, there's going to be no possible mapping for this by G. So the suppose for a contradiction was that this G exists and is surjective. What we're going to show is that, look, the surjectivity part can't be right. I'm going to name a function that G can't hit. So let me write that down. Idea, name a function G can't hit. Okay, so here's my function. D has to be a function. It's good to write down the type first just to keep your head straight. Let me write that arrow a little more neatly. So what's D going to do? It has to take a nat and return a nat. So what D is going to do is it's going to say, you give me a number, call it M. And what I'll do is, well, I'm going to look up the mth function in G. So this is a function itself, right? The G of M is a function of type nat arrow nat. G is a higher order function. So I'm going to call that function on M itself. And then whatever that answer is, I'm going to add 1. Right, so if you like, we can think of this then as H sub M, the mth function, applied to M plus 1. Cool? If G is surjective, then there exists some P such that G of P is equal to D. Right? That's what surjectivity means. What is D applied to P? D of P is going to be G of P applied to P plus 1. But wait a minute, we know what G of P is. G of P is equal to D. So that's going to be equal to D of P plus 1. Now, hold on a dang minute. D of P is equal to D of P plus 1? Get out of town. That, my friends, is a cosmic contradiction. Okay, wild. What just happened here? We said, oh, we're going to show that it's not possible that there's a surjection from the nats to functions from nats to nats. So we said, okay, suppose there was such a surjection. That means we can list all of these functions kind of in order. And then I said, let me come up with this really nasty function that takes the whatever number it's given, looks up into the table that G has, and then sort of contradicts it, right? It does something wrong. And then we see that, look, there's nowhere in the table this can be. Okay, this method is called diagonalization. It's possible to draw a picture of why it's called diagonalization for this theorem, but what I'm going to do is instead prove another theorem that makes it, oops, that's too cosmic. I'm going to prove another theorem that makes it sort of clear why this is called diagonalization. Okay, I'm going to show that R, 0, 1, so this is on the number line, this is this whole range inclusive. Right, it's everything in there. Okay, so this is uncountable. Just to be super clear, these are numbers of the form 0. D0, D1, D2, where each of these are digits. Okay, the proof. It's going to go exactly the same. Every proof by diagonalization goes the same way. Say, suppose for a contradiction that there exists some surjective blah, 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 and then you contradict the surjectivity by finding a counterexample. That's how it works. Okay, so let's see it in action, and then we'll sum up. Suppose for a contradiction that there exists a function, let's call it f this time, from the natural numbers to the real interval 0, 1, that's surjective. Okay, so again, f looks like something like this. 0, here's f, maps to some number 0, and then call it r 0, 0, r 0, 1, r 0, 2, r 0, 3. Right, it's got some, these are all digits, right? Let's make a remark about that. R sub ij are digits, like in 0 through 9. Right, and then, okay, 1 is going to map to 0.r10, r11, r12, r13, and so on. 2, that's going to map to 0.r20, r21, r22, r23. 3, that's going to map to some real number, r30, r31, r32, r33. Right, and you would be justified at this point to be like, yeah, but this will work out. We can just do the path thing, or whatever. But that's not what happens here, right? We're building this matrix, and then what we're going to do is we're going to see, using the diagonal of the matrix, how we can construct an impossibility. Okay, so the proof is going to go the same way as before, same proof idea. Oops, no, give me the actual marker. Thank you. Okay, so the proof is going to go more or less the same way. Sorry, I thought I was muted for a second. The proof is going to go more or less the same way. So first I want to say, let Qij, I'm just going to give a new notation. Q sub ij is equal to, well, if Rij is equal to 4, then it'll be 5. Otherwise, it'll be 4. So this is like a scrambling of the digits. Okay, so I'm going to define a number for you now. Let D, for diagonal, be equal to 0 dot Q00, Q11, Q22, Q33. That's terrible writing. And so on. D is going to be the scrambling of the diagonal. Since F is surjective, there exists some M, f of M equals D. What is the mth digit of D? According to the table, it's R, M, M. According to the definition of D, it's Q, M, M. Okay, this is the beginning of the rumblings of trouble. R, M, M equals, so it would necessarily these have to be equal or we'll have a contradiction. So RMM is equal to, if RMM equals 4, then 5, else 4. Okay. Is it 4? If RNN equals 4, then 4 equals 5, right? Will be in this case. Okay, oh no. Contradiction, can't be that. So RMM, sorry. Did I call it MM earlier? I did, let me fix that. RMM. So RMM is not equal to 4. But then, and so is equal to 4, right? Like then we'd be in this case on the right-hand side. That's another contradiction. So D is not, oh, everybody calm down. So it must be the case that f of m is not equal to d, and f is not surjective. And we get our cosmic contradiction again. Okay, so here, the trick was, it's maybe a little clearer why this is called diagonalization. What is the trick behind Geier-Cantor's idea? This one weird trick just totally frustrates set theorists. They'll hate you if you know this one weird trick. You capture the diagonal, and then you just kind of like wiggle it, right? You mess it up. Right? This is the essence of the proof. And once you've wiggled that diagonal, then you can see that you can produce an element that doesn't show up in your surjective mapping. Now, the key is that you need to be able to build this table where there's something kind of infinite here. You can build a similar table over here thinking about functions, because each of these functions, h sub 0, is itself a table, right? Where you can think of it as two numbers. Like h sub 0 is really a bunch of numbers n00, n01, n02, which sort of saying what the right mapping is for each such number. So you can do a similar diagonalization, and that's exactly what D's doing. I recommend you try to draw this table, but for G as an exercise. What I want to do is sum up. Oops, wrong thing. Diagonalization. One. Suppose for a contradiction, f is surjective. So this is to prove that the cardinality of A is strictly less than the cardinality of B. So f from A to B, surjective. 2. Find a tabular representation. I think that's just a really helpful way to think about it. This isn't mandatory, but to me it's really, really helpful. 3. Find a way to munge the diagonal. What do I mean by munge here? So let me get a nice mungy color out. What's a good munging? Oh, this looks pretty mungy. No, I'm using it elsewhere. Let me get a different. That's not mungy enough. Here, yellow will munge. Right? So here, Qij is our munge. Here, this +1 is our munge. Right? There's just something that you have to flip the diagonal. Define a diagonal value that munges. Right, so the diagonal value we defined, I think in both cases we called D, right? Both of these were our diagonal values. Okay, once you have these parts, see that your value can't be hit by f. That's the recipe. That's the whole recipe of diagonalization. It's an incredibly powerful technique for finding contradictions and sort of this kind of proof. It is just such a powerful tool in your box. To me, this proof technique is at least as cool as Cantor's pairing function, as the sort of the tabular method we saw in the countability proof. It's just such a powerful way of saying no to something that I find it really remarkable. Okay. This video concludes our discussion of countability and uncountability. I hope it made sense to you. Look at the homework. If you have questions, ask on Piazza or over email or in office hours. I have 2 more videos to make for you, just high-level overviews of graphs and their terminology, and I'll have those coming at you soon. Okay, hope everybody's doing all right. Talk to you soon.